Welcome to all of you. Now we discuss about multiple choice question of the paper CC-5 Mathematics Honors, University of Calcutta, 2019. In the question paper 2019 CC-5 paper Group A, question 1A, let phi x equal to limit n tends to infinity fx plus gx whole divided by x to the power n plus 1 f and g maps real number r to r are functions. If mod x greater than 1, then phi x is equal to what? Actually, this question I may be wrong because the power of this n. Answer is this. Equals to fx. If minus infinity less than x less than minus 1, then as n tends to infinity, mod of x to the power n tends to infinity monotonically, but x to the power n does not have a limit as n tends to infinity, because if n is even or odd, so mod x to the power n tends to infinity, but x to the power n does not have a limit as n tends to infinity. If power n is odd, then tends to minus infinity, x tends to infinity, so does not limit this. If x is negative, so this if n is odd, then tends to minus infinity. If n is even, then x to the power n tends to infinity. So x to the power n does not have a limit as n tends to infinity. If x is this 1 less than x less than infinity, then n tends to infinity, x to the power n tends to infinity monotonically. So obviously limit n tends to infinity 1 by x to the power n equal to 0. Now phi x equal to limit n tends to infinity fx plus gx by x to the power n whole divided by 1 plus 1 by x to the power n, and dividing numerator and denominator by x to the power n, we get this gx by x to the power n tends equal to 0 and 1 by x to the power n equal to 0, so this is equal to fx. If this 1 less than x less than infinity, but we cannot find for this minus infinity less than x less than minus 1. So we correct this question in this form if we phi x equal to limit n tends to infinity x to the power 2n fx plus gx whole divided by x to the power 2n plus 1. Then obviously this x to the power 2n, this tends to infinity if this limit mod of x greater than 1. So mod of x greater than 1, then when x is 1 less than x less than infinity and minus infinity less than x less than minus 1, this range. And if limit in this to infinity x to the power twice n equal to 0 if mod x less than 1, and this tends to infinity if mod x greater than 1, and this equal to 1 if mod x equal to 1. Now we are interested for the ranges mod x greater than 1. So obviously limit n tends to infinity 1 by x to the power 2n equal to 0 for mod x greater than 1. So dividing numerator and denominator by x to the power twice n, we get this gx by 2 x to the power 2n equal to 0 and 1 by x to the power 2n equal to 0, so this is equal to fxn. Next question. Question B. Log to the base e box x is continuous on, answer is these two, open interval 1, 2. Actually, this box x means the floor of x. So box x function equal to 0 when 0 less than equal to x less than 1. So this is the graph. And box x equal to 1, greatest integer function, that is the floor x, if 1 less than equal to x less than 2. So this is the box x value is 1 within the limit 1 and less than equal to x less than 2, and so on. And for box x equal to -1 for -1 less than equal to x less than 0. So obviously log to the base e box x is undefined if 0 less than equal to x less than 1, because log 0 is undefined, so this is undefined for this limit. And log this box x equal to 0 when x is 1, and that is 1 less than equal to x less than 2. Log 1 equal to 0. So 1 less than equal to x less than 2, this is the 0. So this is the graph of this within this interval. And if x 2 less than equal to x less than 3 within this limit, then log 2, this is 2, so log 2 equal to this, log 2 to the base e. So we get this is log 2, this is the log 2, this is the graph. Now log x is continuous. Obviously this -1, 1 within this open interval, there is no value for log of box x to the base e, and in this within the open interval of 1 and 2 we get this is the value 0. This is the continuous within this open interval, and obviously not continuous within this interval 0 to infinity, and obviously not continuous this. So correct answer is this, within this two open interval within 1 and 2. Question C. If f maps closed interval AB to R is continuous on the closed interval AB such that f of A less than f of B, then what is the correct answer? The correct answer is 2. Here f is this continuous function within this interval, closed interval AB to R. This point A, this is the graph of fx. Say this is the graph of fx. So when point A, so f of A is the value is this f of A, and B, value of a B is this, say. So f and a B is this value. So we can find this the minimum value. This is the minimum value infimum of this graph of this curve within this interval, this small m, and this is the supremum, the maximum here is the capital M is this here. So actually this is this f FA and FB, FA and FB, this closed interval is a subset of f of the closed interval AB. Actually, f of the closed interval AB means this small m to capital M, small m to capital M closed interval. So obviously, FAB, this interval is subset of this interval of this here. So correct answer is 2. Question D. Let F maps R to R be defined fx equal to x sine 1 by x not equal to 0 is 0, x equal to 0. Then oscillation of f at 0 is, correct option is 4. Actually, oscillation, what is oscillation? Oscillation of f on an open set, be a real valued function of a real variable. The oscillation of f on an interval I in its domain is given by omega ff I equal to supremum fx x belongs to I minus infimum fx x belongs to I. An oscillation of f at a point of a real variable at point C is given by omega f c equals to limit epsilon tends to 0 omega f c minus epsilon comma c plus epsilon within this open interval. For this, c is positive, a small positive quantity. So for example, fx equals to 1 by x for this graph. So has oscillation at infinity at x equal to 0. X equal to 0. This is the plus infinity when x tends 0 plus, 0 minus, the minus infinity. So oscillation is infinity. And oscillation is 0 at any other x because except 0, r minus 0, this function 1 by x is continuous always except the point 0. So oscillation is 0. And for the function sine 1 by x has oscillation 2 at x equal to 0 and 0 elsewhere, because at the point 0 we get the supremum value is 1 and infimum value minus 1. So supremum minus of minus infimum is equal to 1 minus minus 1 equal to 2. So sine 1 by x, oscillation of sine 1 by x at the point 0, x equal to 0 is 2. And if x equal to sine x has oscillation 0 at every finite x, because almost sine x is continuous throughout x, and 2 at minus infinity to plus infinity. And fx equal to minus 1 to the power x has oscillation 2. Now here the function is x sine 1 by x. This is the x sine 1 by x, x in the Desmos graph, sine 1 by x. And this is the graph of this. So the beautiful graph is this. This is the x-axis, this is the x-axis, and this is the y-axis, this is the y-axis, this point is origin. So this is the to this, and if we enlarge this graph, we get this. So this is the graph of x sine 1 by x. This is the graph of x sine 1 by x, and at this point 0, this point, this graph x sine 1 by x is the continuous, this. So oscillation is 0. Because we have theorem, if f maps interval I to R is bounded and C belongs to I, then f is continuous at C if and only if the oscillation omega f c equal to 0. So f is bounded and C belongs to the interval I. And if f is continuous, then oscillation is 0. And if oscillation is 0, f is continuous. So obviously, limit x tends to 0, x sine 1 by x equal to 0 equal to f0. So at the point x equal to 0, this function x sine 1 by x is continuous. Hence the oscillation omega f 0 equal to 0. Now the definition of Saltus, actually this is the oscillation. We can define this EMF, capital MF C equal to maximum of F supremum FC plus 0 upper bar, FC plus 0 lower bar, FC minus 0 upper bar, FC minus 0 lower bar, and small fc is the minimum of these four elements. And then the Saltus of F at C, SFC equal to capital MFC minus small fc, that is the oscillation of this function. So here for sine 1 by x, this f 0 plus 0 equal to 1 when we approach 0 from the right hand side, and this limit supremum is 1 and limit infimum is minus 1 here from the approach to 0 from the right side. And when approach to 0 from left side, that is 0 minus 0, upper bar limit supremum is 1 also, and 0 minus 0, the limit infimum equals to minus 1 also. So the maximum of these four real numbers is 1 and minimum is minus 1. So omega 0 Saltus this capital MF minus small mf, that is equal to 1 minus minus 1, that is equal to 2. So obviously oscillation of this function at the point 0 is 2 for sine 1 x. But x sine 1 by x equals to 0. Oscillation is 0. Next question. Question E. And G maps from the closed interval 0 to 1 to the real number R, set of real numbers R, be defined by Gx equal to 1 by n if 1 by n plus 1 less than x less than equal to 1 by n belongs to set of natural numbers n. And this Gx equal to 0 if x equal to 0. Then the set of points of discontinuity of G is, correct answer is, and in 3, an enumerable set. Clearly, Gx equal to 1. If we put n equal to 1, this 1 by 1, that is 1, 1 by 2, that is half, less than x less than equal to 1. If we put n equal to 2, we get Gx equal to 1 by 2. The range is 1 by 3 less than x less than equal to half. If we put n equal to 2, we get Gx equal to 1 by, n equal to 3, we get Gx equal to 1 by 3, and the range is the 1 by 3 plus 1, that is 4, less than x less than equal to 1 by 3, and so on. And this is equal to 0 if x equal to 0. So we get the graph this within this limit 1, this 0, x-axis, this half. So half and 1 is the semi-closed interval. Half is open and 1 is closed. So this 1, this value is 1. This constant with this interval, this. And piecewise function. And this point piecewise continuous. This 1 by 3 and half. So 1 by 3, this is the half. Gx equal to half. So this is the value half. Is 1 by 3 and 1 by 2. 1 by 3 is open and 1 by 3 is closed. And so next interval 1 by 4 to 1 by 3 semi-closed interval value is 1 by 3, and this point 0, 0. So set of point of discontinuity of G is given by, obviously within this interval 0 to 1 closed interval. So we get this half, obviously discontinuity, jump discontinuity, and 1 by 3 there is jump discontinuity. So the point of discontinuity of G is given by within this interval 0 to 1 is half, 1 by 3, 1 by 4. Obviously this maps to natural number n. So this is the set is enumerable or denumerable or countably infinite, as there is a bijective mapping F maps set natural number N to S. So this is the enumerable set. Next question. Question F. Let F maps set of real numbers R to R be defined by fx equal to x if x is rational and 0 if x is irrational. The type of discontinuity of F at x equal to 1 is actually is the question answer is 1, oscillatory discontinuity. Now mod of fx minus f0, that is equal to mod of fx, because f0 equal to 0. So mod of fx equals to mod of x if x is a rational number, set of rational numbers q, and this equal to 0 if x is irrational number. So this is equal to this. So for epsilon greater than 0, we get mod of fx minus f0 is less than epsilon for all x belongs to this 0 minus epsilon, 0 plus epsilon. So f is continuous at 0, which continuous at 0. Let c belongs to R in real number and c is non-zero. Let us take a sequence of rationals xn such that xn greater than c for all n belongs to natural number, set of natural numbers n. Limit x tends to xn tends to infinity equal to c. Because here this xn set of rational numbers, so we get this fx equal to x if x is rational. So this xn sequence of xn, so limit xn equals to c, xn equal to c, xn tends to c, and then because xn is rational, so xn is rational, so this is the limit tends to infinity if xn equal to limit xn tends to infinity this xn c. We take the rational set of sequence of rationals xn, and such that limit xn tends to infinity equal to c, when xn is greater than c. Let us take another sequence of the irrationals yn, such that limit yn equal to c for yn greater than c for all n. Then this irrational number, so for irrational number fx equal to 0 for irrational number, so we get limit fyn equals to 0. Hence limit fxn equals to c, limit fyn equal to 0. Hence limit fx does not exist, as for two different sequence xn and yn within this interval c to infinity, both converging to c, then the sequence fxn and sequence fyn converges to different limits. And similarly, we can find limit x tends to c minus fx does not exist also. Hence, f is discontinuous at c, and it is a discontinuity of second kind, that is oscillatory discontinuity. At least one of the limit fx x tends to c minus and limit fx x tends to c plus does not exist, but f is bounded. F is bounded here. This f is bounded here. Fx is rational x and 0. So if fx is bounded, so at least one of these does not exist. Here limit x tends to c plus fx does not exist. At least one of them. But if f is bounded on this deleted delta neighborhood of c, n dash c delta, and f is defined at c or not, f may be defined at c at the point c or not, then this type of discontinuity is called oscillatory discontinuity, and this is the discontinuity of second kind. Next question. If f maps close to interval 0 to 1 two set of real numbers R is differentiable on the closed interval 0 to 1, and if 0 equal to f1, then correct answer is 4. F dash x equal to 0 for some x belongs to 0 and 1. F is differentiable on this closed interval, and so F is continuous on this closed interval 0 to 1 and differentiable within this open interval 0 to 1, because this is the condition for Rolle's theorem. So obviously we get these two conditions this. Now f0 equal to f1. So third condition also satisfied this. Hence by Rolle's theorem, there exists at least one point C within this open interval 0 and 1 such that f dash c equal to 0 within this open interval. Hence option 4 is correct. Question 8. Fx equal to 3 plus 2x minus 3 by 2 less than x less than equal to 0, 3 minus 2x 0 less than x less than 3 by 2, and the correct answer is 2. Continuous but not differentiable at 0. Here fx equals to 3 minus 2x within interval minus 3 by 2 less than x less than 0. So minus 3 by 2 0, this semi-closed interval 0, this 3 plus 2x, this is the graph of 3 plus 2x within this of semi-closed interval. And when x 0 less than x less than 3 by 2, we get 3 minus 2x, 3 minus 2x. This is the opening interval. So this is the opening interval. Now, at the point 0, limit fx extends to 0 minus from the left side. We get from the left side, the value of fx is this 3 plus 2x. So x tends to 0, so we get this 3. This is the value 3. And right hand limit extends to 0 plus fx. So 3 minus 2x, this is equal to 3. So left hand limit equal to right hand limit. So the limit exists at the point x equal to 0. But f0 equal to 3. f0 equal to 3 because here f0 is x equal to 0 is 3 also. So right hand limit equal to left hand limit equal to the functional value of that at that point 0. Hence, obviously, this limit extends to 0 fx equals to f0. Hence, fx is continuous at x equal to 0. But this is not differentiable because if we find limit extends to 0 minus fx minus f0 by x minus 0, this x minus 0 minus, so we get 0 minus is this 3 plus 2x, 3 plus 2x, f0 equal to 3, we get 2. This is the left hand derivative is f dash 0, value is 2, and right hand derivative this the fx equal to 3 minus 2x minus 3, this minus 2 right hand derivative. So left hand derivative not equal to right hand derivative, hence it is not differentiable at x equal to 0. So correct option is 2, continuous but not differentiable at x equal to 0. Question I, the region of validity of the infinite series expansion log 1 plus 3x to the base e about x equal to 0 is correct option is 1. Minus 1 by 3 less than x less than equal to 1 by 3. The region of validity of the infinite series expansion of log 1 plus ax to the base e a not equal to 0 about x equal to 0 is minus 1 less than ax less than equal to 1. That is minus 1 by a less than x less than equal to 1 by a. And the series expansion is this: log 1 plus ax to the base equal to ax plus minus ax square by 2 plus ax cube by 3, and so on, so on. That is the infinite series summation n equal to infinity minus 1 to the power n plus 1 ax to the power n by n not equal to 0. If mod of ax greater than 1, this the limit tends to infinity, this mod this equals to infinity, and the series diverges. If ax equal to minus 1, and we get the divergence series, ax equal to minus 1, we put ax equal to minus 1, we get actually minus 1 by n series, minus 1 minus half minus 1 by 3. Obviously it is a divergence series. If ax equal to 1, and then we get 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, and this to infinity. Then it converges by Leibniz test, and if mod of x less than 1, it converges absolutely. This is the series mod of x to the power n by n. That is minus 1 less than x less than equal to 1 for convergence series. Hence the limit actually 1 by minus 1 by a less than x less than equal to 1 by a. So here a is 3. So obviously correct option is 1. Minus 1 by 3 less than x less than equal to 1 by 3. Next, last question J. If x equal to 3 minus x into bracket x minus 1 has a local maximum at correct option is 2. Here 3 minus x, x minus 1. Actually, this graph can be drawn from Desmos app. This bracket 3 minus x to bracket x minus 1. But sorry, this is the graph. This is the graph. This point is vertex point is 2 1. This 1 0 point, and this point is 3 0. And this is the graph of this parabola. So we get this graph, this, and obviously if x equals to 4x minus x square minus 3, expanding this, f dash x equal to 4 minus 2x, f double dash x equals to minus 2 is negative, and f dash x equals to 0 gives x equal to 2. So for x equal to 2, we get f double dash x equal to minus 2, negative. So obviously f has a local maximum at x equal to 2. This completes the MCQ answer of the real analysis part, and thank you.